Hi, folks. Today I'm going to teach you about the mole in chemistry. The mole is not any of the things that you see here, but it is a unit, a quantity in chemistry that helps us to answer questions like, how many water molecules are there in a drop of water? How many do you think? There are a lot of molecules in a drop of water because molecules are so small. And we need the mole to be able to talk about these kinds of numbers because we will have a lot of molecules. One mole is also known as Avogadro's number. And one mole is this many items. This is 602 sextillion 200 quintillion items. That's a lot of items. And it's not, by the way, it's not a dirty word. We're talking about 602 sextillion items. Now, how would we use the word the mole, one mole? Well, just like for eggs, when we talk about 1 dozen of eggs, 1 dozen stands for 12. So if I have 1 dozen eggs, I have 12 eggs. If I have 2 dozen eggs, that's 24 eggs. So just like we use the word dozen, we're going to use 1 mole. 1 mole is this many items. So I could say I have 1 mole of eggs. And that would be this number of eggs. If I had 2 moles of eggs, I would have 2 times this number. And so that's how we use the word. It's just a word to stand for a number of things. And these things can be anything. They can be eggs, they can be atoms, they can be molecules. We usually use it to refer to a number of particles, which is usually molecules or standalone atoms. So when it comes to talking about the water droplet, when we talk about a mole of water molecules, we're talking about this number of water molecules. Now, there's an easier way to express this number using scientific notation. What is scientific notation? Well, I would boil this down to a number between 1 and 10. Actually, let me give you an example of scientific notation. Let's start with the number 10. In scientific notation, I take a number that's between 1 and 10, be smaller than 10, greater than or equal to 1, and I multiply it by 10 to the power of 1. So this is equal to 1 times 10, which is equal to 10. Let me show you another one. Let's say I wanted to express the number 100. This would be equivalent to 1 times 100, which is equivalent to 1 times 10 to the power of 2. And by the way, if you didn't know, 10 to the power of 2 is 10 times 10. Just like 10 to the power of 3 is 10 times 10 times 10. So 10 to the power of 2 is 100. 10 to the power of 3 is 1,000. And so I can express these numbers in scientific notation by doing 1 times 10 to a certain power, where this number shows me the number of zeros that I have here. And it also shows me the number of times that I jump in order to get my number. Here I'm jumping twice. Let me just do one more. 1,000 is 1 times 10 to the power of 3. And this is the same thing as 1 times 1,000. And it's the same thing as taking 1 and jumping 3 times and putting 3 zeros on it. So when I read scientific notation, I take this number and jump to the right this many times, adding zeros. The mole, this number, can be boiled down to 6.022 times 10 to the power of. And I would start here and jump this many times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. It's 10 to the 23rd power, jumping from this decimal place. And we usually round to just 2 decimal places, so I would round down. And the moles usually expressed as 6.02 times 10 to the 23rd. And we're talking about items, usually molecules, and this is equal to 1 mole. Before we do any calculations with this number, what I want to do is walk through just imagining how many items this is. And I want you to imagine what would it look like if we had 1 mole of peas. How much room do you think this number of peas would take up? Well, let's take a look. If I had 1 times 10 to the 2nd power, or 100 peas, that would take up 1 cubic inch. That's a cube that's an inch on each side. And you probably would have to smash the peas together to fit 100 peas in there. Well, if I had 1 million peas, that's 1 with 6 zeros, 1 with 6 zeros. That would take up the size of about a refrigerator. That's 1 million peas. That's 6 zeros. What about a billion, 1 with 9 zeros? It would take up the size of an entire home. Do not try this at home. A whole house? Yes, a billion peas would cover the entire house. What about 1 trillion? 12 zeros, that's about 1,000 houses, or the size of a medium-sized town. But are we close to 1 mole of peas? Not even close. Okay, what about 1 quadrillion, which is a 1 with 15 zeros? That's a lot of peas. That's enough to fill all of the buildings in Denver with peas. Are we still close to a mole of peas yet? No, not even close. Not yet. Okay, what about 1 quintillion? 1,000 times more. 1 with 18 zeros. That would be enough to cover the entire state of Colorado, nearly 16 feet deep. But we're not even close yet. It would look something like this. The entire state of Colorado, 16 feet deep in peas, would be 1 quintillion peas. And that's not even 1 mole of peas. So a sextillion, which is 1 with 21 zeros, that would be enough peas to cover the continents of the world 4 feet deep. That's all the continents 4 feet deep. So look something like this, all of them. And it's not yet close to a mole because that's only 21 zeros. So what about a mole of peas? Well, that's about 1,000 times more, or 100 times more. That would be 250 planets, the size of Earth, covered completely with 4 feet of peas. That would be 1 mole of peas. Give or take a few peas, of course. It would look something like this. 250 planets covered 4 feet deep. That would be a mole of peas. So what if I had the same number of peas as the number of atoms in my body? How much size would that take up? How many atoms do you think we have in our body? How much size do you think that number of p's would take up? That would be a cotillion p's, 1 to the 27th power, and that would be 4 feet deep, covering 250,000 planets the size of Earth. So a mole is a really big number then, and everything that has a mole must be big, right? No, because atoms are very, very, very small. Okay, before we get into some quick conversions about the mole, let's take a look and just do a quick review about dimensional analysis and unit conversion. That when I multiply numbers, if there's no fraction, it's like it is on top of the number 1 or just on top. And when I multiply fractions, the tops and the bottoms, if they have the same unit, they will cancel out. And so my ending unit would be this orange circle here. This is how I do unit conversion. On this example, the top and bottom here, when I multiply, cancel out. And I know that the unit that needs to go here is the same as this donut, so it cancels out. So my final unit is correct. Use what we just learned to calculate and use the mole. This question says a sample contains 4.7 moles of xenon gas. How many atoms is that? Well, to figure out how many atoms are in 4.7 moles, I start with my given. 4.7 moles of Xe gas. Notice how I just abbreviate moles as MOL. And just like at the beginning of the year, we're going to use our bunk beds. And on the bottom, I put moles of Xe gas. Remember, whatever unit I have up top here is going to go on the bottom in the next room, or of the bottom of the next bunk. And I'm going to go from moles of Xe gas to atoms of Xe gas. And I know for every 1 mole of Xe gas, I have 6.02 times 10 to the 23rd atoms of Xe gas. So I just multiply the tops and divide by the bottom. And I'm going to bust out my TI calculator for this. Look at how, so I do 4.7. There's a couple of ways that I can do this. I can do times 6.02, and the most traditional way is to do times 10 to the power of. So I'm going to do times second, click 10 to the power of 23, and then that will give me my number. But there's an easier way to do this. If I do 4.7 times 6.02, instead of doing all this, I could do second EE, and this EE is like times 10 to the power of 23. So when I write my answer, this would be 2 point, and I'm going to always round to 2 decimal places, just like we did at the beginning of the year. 2.83 times 10 to the 23rd Xe atoms. So 4.7 moles is that number of atoms. Some people ask if they can write 2.83 E 23. I am still currently not okay with this. Probably one day I will be, but for now, I want you just to do times 10 to the power of 23. Okay, let's do another one. It says a sample contains 5.8 moles of H2O. How many molecules is that? Well, I have 5.8 moles of H2O, and I want to convert that to molecules. So I'm going to use my bunk bed. And when on the bottom is going to be moles of H2O, and I'm going to molecules of H2O. Now remember, if I have 1 mole, that's 6.02 times 10 to the 23rd particles. That's usually atoms or molecules, whole standalone particles, depending on what we're looking at. So I know 1 mole of H2O is 6.02 times 10 to the 23rd molecules of H2O. It's always this number for 1 mole. And so if I put this into my TI, I'm going to do 0.58 times 6.02, and I'm going to do my second EE 23, and that gives me 3.4, looks like it's 9, times 10 to the 23rd H2O molecules. And notice how moles of H2O cancel out and H2O molecules are what I have left. And I'm going to also box my answer. Okay, so back to our original question. How many molecules are there in a drop of water? Well, we first need to in order to answer this, we need to learn about something called gram formula mass. Or it's also known as molar mass of water. Water is H2O. It has 2 H's, 1 O. When I look at H on the periodic table, this is what I see. It turns out that this number right here is the mass in grams for 1 mole of hydrogen atoms. Let me just say that again. 1 mole of hydrogen atoms equals 1.008 grams. And for oxygen, 1 mole of oxygen atoms is this many grams. In other words, H is 1.008 grams for every 1 mole. This is the unit we will be working with when it comes to molar mass. And oxygen is 15.999 grams for every 1 mole. 1 mole is that many grams. So I can add up 2 H's and 1 O to see how many grams for 1 mole of H2O molecules is how many grams is 1 mole of H2O molecules. And I do that by adding up these masses, these numbers for H and O. So I do 1.008, which is 8 H, and I have 2 of them, plus 15.999. If I put this into the calculator, 1.008 times 2 plus 15.999, it gives me 18.015. And the units here are grams per mole, because that is the unit when I deal with molar mass. So each of these, we talked about earlier in the year about how this is atomic mass units. It's also grams per mole. So when I add up the grams per mole for 2 hydrogens and 1 oxygen, I get a total of 18.015 grams for every 1 mole of water. That means 1 mole of water, which is 6.02 times 10 to the 23rd molecules of water, that is equal to 18.015 grams. And when it comes to a drop of water is 0.05 grams. So we can convert all the way to molecules by starting with 0.05 grams of H2O water. And I know for every 18.015 grams of H2O, I have 1 mole of H2O. And I know, and I'm not going to stop there because grams will cancel out, but I want to get all the way to molecules. For every 1 mole of H2O, I have 6.02 times 10 to the 23rd molecules. How would I put this into the calculator? I would multiply these top numbers and then I would divide by each of the bottom numbers. Let me show you. I would do 0.05 times 1 times 6.02 EE23 divided by 18.015 and then divided by 1 again. And that gives me 1 point, I'm going to round to 2 decimal places, 67 times 10 to the 21 H2O molecules. That's how many molecules are in one drop. And that's a lot. That's 1 sextillion. That's a lot. And, okay, the biggest takeaway from here, for those of you watching from home, is, in learning from home, is how to calculate gram formula mass. To calculate molar mass of H2O, which is in grams per mole, I add up 2 H's and 1 oxygen. That gives me a number of 18.015, and the units for that is grams per mole. And I know that 1 mole of water is this many grams, and that's also this number of molecules. We also learned today about calculating going from moles to atoms, how big a mole of P's, or how big of a number moles are, and that is our lesson for the mole.